This video is on topic 2.4, the structures of metals and alloys. And today we're going to talk about particulate representations of both metals and alloys. My name is Alice Pudi, and this is the last video that I'm going to be doing in Unit 2 for AP Daily. In a previous unit, we talked about metal bonds and the fact that metals contain positively charged ions with a sea of mobile electrons. So what we have here are my positively charged ions, so my cations, and these electrons, instead of being attached to one atom, are actually free to move around all of the different metals atoms that we have here, and that's what makes these delocalized electrons. And it is the attraction between the cation and these electrons which make this metallic bond. And because of this, metals have unique properties in that they're good conductors of electricity, they're malleable, and they're ductile. And in a later unit, you will learn about those properties a little bit more. In the last video, we took a look at ionic compounds and why ionic compounds conduct electricity. And so these will conduct electricity because they have charged particles and the particles are free to move. And in this case, it is the cation and anions that can both move. Now, metals can conduct electricity as well, but for a different reason. And it's because the electrons are capable of moving, and that's what allows it to conduct. For alloys, alloys are the combining of two or more metal elements, and there are two types of alloys. So the first kind are substitutional, and for a substitutional alloy such as brass, you're going to have two elements that are similar in size. And so in this case, brass's base element is copper, meaning the majority of it is copper, and then zincs have been substituted in for some of the copper atoms. And notice that this means that they're similar in size, but not necessarily the exact same size. Substitutional alloys then are alloys for atoms that are very different in size. So in this case, iron is the base metal, and carbon, which is significantly smaller, isn't substituted in for an iron atom, but actually fits in the spaces between the iron atoms. Right. What I'd like you to do is read this question and then answer it. So press stop, complete that, and then press play when you're ready to begin. For this particular alloy, if we take a look at the sizes of the atoms, you can see that again, they're similar. And so because they're similar, this indicates that this should be a substitutional alloy. And so picture B would be a reasonable representation of our substitutional alloy. Now that we are told that we have an interstitial alloy that's made of two elements, which are X and Y, where Y is the base element, and that the alloy is 20% X and 80% Y. And now you're asked to draw the diagram given that the representation has 10 particles. So please press stop, draw your diagram, and then press play when you're ready to continue. Since this is an interstitial alloy, that means that one of the atoms has to start filling in the spaces between the other elements that are in your structure. And so since our compound is 20% X and 80% Y, X is going to fill in the structure, and we had to have 10 particles. So notice that I have 8 of them that are Y and 2 of them that are X. Now your particle arrangement doesn't have to look exactly like this, kind of 4 across and 4 across, but it does have to have the X's filling the spaces in between the Y's, and you do need to have this ratio of 2 X's to 8 Y's. This is the end of the video. Thank you for watching. This is the last video, as I mentioned before, that I'm going to do for AP Daily for Unit 2.